So I'm Mike Stonebreaker, and I'm here to tell you about a database operating system.
Oh, okay, hold on.
So I'm going to do this historically, and I'm going to tell you about the MIT Stanford Research Project, which started in 2020 and was ongoing until the end of last year. And it had two phases that I'll tell you about. And starting at the end of 2023, we started on a commercial venture to make this available commercially. So the first version will be available next month. The SDK is available now. So the context from which this project began is Linux is 40-ish years old. So it is elderly software, it's legacy code. And the way you can tell is progress has slowed a lot. So there's still no multi-node version of Linux. And Linux is full of security holes. It is a leaky boat, as everyone will admit. So it's time to send it to the home for tired software. But that's not the main reason why I want a new operating system. And the main reason is scale. In the last 40-ish years, the operating system state, which you have to manage, which is processors, memory, storage, tasks, messages, files, all that stuff, has gotten massively larger. So when I started using Unix in 1974, it was on one processor with 48K of memory. One of the environments in which DBOS runs now is on the MIT supercloud, 32,000 processors, many terabytes of main memory, 10 to the 6th bigger. So that makes managing OS state a database problem without me saying another word. However, the reason to initiate this project was I went to a talk by Matej Zaharia, who's the founder of Databricks, also on the faculty of Stanford. And schedule a million things. And he said that is hopeless using traditional scheduling technology. He put his scheduling information into a, wait for it, a Postgres database, and was whining about Postgres performance. So I said, we can do better than that. And that's exactly what we've done since then. So in my opinion, in 2020, it's time to rethink the operating system from the bare metal up. So in a nutshell, what we're doing is traditionally all database systems run as an application of the operating system. That's not the way DBOS runs. The operating system is an application of the database. So you have to invert your thinking, turn it on its end, turn it 180 degrees. So you need to rotate your thinking 180 degrees. What does that mean? What did you do? What did you do? Specifically, here's the way DBOS looks. It has 4 levels. Level 4 is user programs and user space, just like you've come to know and love. And then you enter the operating system through a protection boundary. And at level 3, you get OS support routines, things like change directory, open file, send a message. We're fine now. So one level down is a multi-node, multi-core HA, transactional, serializable. Tables are segmented over multiple nodes, et cetera, et cetera. VoltDB is what we're used in our research prototype. And the thing to keep in mind is that OLTP database systems have gotten massively faster in the last decade or so, and that enables this whole architecture to work. And the database system runs on the bare metal, i.e. it runs on a microkernel. Think of it as OSP or Firecracker, something like that. So that's the architecture. Pictorially, if you want to think in pictures, you run effectively on a microkernel. The only thing running on that microkernel is the database system. And above that are a bunch of database applications implementing operating system services. And above that are the applications you come to know and love. Okay, so that's what we have. If you want to summarize our point of view, Unix was revolutionary in the 70s by saying everything is a file. The way you communicate between anything and anything is using a file motif. So the old mantra is everything is a file. The new mantra is everything is a table. The way to think about DBOS is everything is a table. We don't see any advantage to a more complicated data model. And all, I mean all, every single bit of operating system state is in the database system in tables. Okay, so what does that get you? Well, operating system state is in tables. So if you want to know anything about what's happening with the operating system, that's just a SQL query. So analytics are much better and easier and much more flexible. If you want to monitor the state of your system, again, that's in SQL, much easier, much more flexible. This is a multi-node operating system because the database system is multi-node. There's no reason for Kubernetes or some other orchestrator. So Kubernetes is gone, Linux is gone, and you get transactions for all operating system state for free. You get HA for operating system state for free, no need for separate high availability system. So life is good. And so when I presented this to operating system aficionados, they of course feel very, very threatened because it's the database guys horning in on their turf. So they can't argue that this is more functional and more flexible than what they're currently doing. So they resort to, you can't possibly make this fast enough. Well, I've heard that argument before from the naysayers of relational databases. So the simple answer to, can this be fast enough? The answer is yes, it is fast enough. And we spent the first year and a half proving that. So in phase 1 of the DBOS research project, we implemented a file system in SQL. We implemented interprocess communication, i.e. messages, in SQL. We implemented a bunch of schedulers, all of this on top of VoltDB, running on either the MIT SuperCloud or on GCP. So that's what we did. And what happened? Well, before I tell you what happened, I want you to really get clear on what's going on. So the message system. The message system is one table called the message table, has 3 fields, a sender, a receiver, and a payload. It is partitioned on receiver ID. So if you want to send a message, it's simply a SQL insert into this table. That's it, nothing more. If you want to read a message, when you send a message, the database system, since it's partitioned, will move that tuple to the site of the receiver. And so to read a message, you just do a SQL query, followed by a delete if you don't want to keep the message. So the message system is all in SQL. There's nothing else. And of course, this is really flexible. So if you want to send the same message to two people, you simply do two SQL inserts, and you get multicast fairly trivially. So just to make this really stick, what's the file system? It's a file table, a directory table, and a table to store the blocks. And so if you partition the block table on owner, you basically get a file where all the blocks are on one node. You get something that looks like the Linux file system. If, on the other hand, you partition the blocks table on block ID, then that will spread the blocks all over everywhere, and you get a parallel file system with very similar behavior to the Lustre file system, which is a parallel file system that is the MIT supercloud users are enamored with. So if you want to change the file system behavior, you just repartition. Again, it's a trivial operation. So very flexible. So we wrote a paper that appeared in VLDB in 2022. And scheduling DBOS is more or less competitive. It's about the same performance as whatever you're currently doing. IPC is fairly competitive. File system is competitive with both Linux file system and with Lustre. So basically, this will run exactly as fast as whatever you're currently doing. So there's no performance loss to doing what I'm talking about. Okay, so that gave us the courage to keep going. So in phase 2, we implemented a provenance system, and we implemented a serverless environment, which I'll tell you, both of these I'll tell you about. So what's provenance all about? You keep a record of everything that's happened. So all operating system state is in the database. So you simply log changes to the state of the database. So that will generate a record of all operating system events. And this is standard database log processing, well understood by database folks. So provenances keep a record of everything. And applications should do the same thing, which is keep a record, store interesting state in database tables, and then you get automatic provenance for such state without you having to do anything. So app level monitoring comes by just putting application state also in the database. Okay, how do we implement this? Well, the last thing you want to do is store this log in a main memory database system like VoltDB. So we spool the log transactionally into a data warehouse. Think Vertica or Redshift or Snowflake. Any one of the column-oriented data warehouses would be fine. So you can run any SQL query on history that suits your fancy. This costs you 5% at runtime. So the cost of keeping everything is not gigantic at all. So what happened? Well, we tried running this against the system that everybody loves to hate, namely Splunk. So if you want it, and so the two things that we did, one is application state goes into the database, gets transactionally spooled to the warehouse. That's what we do. If you want to use Splunk, well, we wrote a Splunk adapter that would capture state changes from the database, namely VoltDB, into the Splunk world. Those get converted to CSV, and then Splunk deals in CSV and then compresses it and runs and then stores that in Splunk storage and you write queries in Splunk Talk. So ingest is faster because there's no need to convert stuff to CSV. It's binary all the way. Queries are wildly easier to write because SQL is much more accessible than Splunk Talk. And data warehouses are awfully good at these historical sorts of monitoring queries. So queries are faster and wildly easier to write. So basically, this is all goodness. This runs faster, and you avoid a 7-digit-a-year subscription to Splunk. So net of what we said so far is automatic logging of all OS state. If it's fast enough for the operating system, it ought to be fast enough for your application. So log everything into the database and then keep it for a while. And then you query the provenance information in the data warehouse for outliers in SQL instead of Splunk Talk, or write an ML application. That would be fine too. That's clearly a better idea than using SQL. And then the great thing about this system is if you get a ransomware attack, then it's a while before you notice, say 15 minutes. So then you take action. And now your computer system is a mess. So you've got to get back up. And Splunk has no facilities to help you get back up. On the other hand, in DBOS, you just rewind everything 16 minutes, single step around the problem, and then keep going. So you get back up in seconds to maybe a minute. And of course, you can restart at from any point. So you don't, if you got a bad application error 9 minutes ago, you just back up to before that, and then single step forward. So frosting on the, so in terms of security monitoring, it's easier and faster than traditional tools. And the frosting on the cake is you get automatic recovery. Okay, so how do you program in DBOS? Well, I don't have to tell you this. Everyone knows everything but everything is going to the cloud for obvious cost reasons. How do you know that? Well, James Hamilton, AWS wizard, says he can stand up a server for 25% of your cost. And there's no reason for me to disbelieve him. Azure data centers, last time I looked, which was like 2 or 3 years ago, they are shipping containers in parking lots. So chilled water in, power in, internet in, otherwise sealed. If boards go bad in the shipping container, you just configure them out. If enough boards go bad, you bring in a crane, take away that shipping container, replace it by another one. So there's no possible way that you guys running raised flooring in Cambridge can possibly compete with this sort of stuff. So also, they are deploying servers by the millions, you're deploying them by the thousands, they're way down the cost curve relative to you. So they have a huge cost advantage. And so the world is going to move to the cloud. Moreover, if you look at the pricing of AWS or GCP or Azure, everybody is encouraging you to run software as a service, function as a service, serverless environment, call it whatever you want. And so if you structure your application as a graph of stateless, call them micro operations, passing results as arguments to the next function in line or through storage, think in AWS, think S3. If you structure your applications that way, then you only pay for computing while you're actually running. You're not having to pay for idle capability. And AWS Lambda OpenWhisk lead the way. This is the future of how to do cost-effective computing on the cloud. There's no reason to expect this to change. So I expect SaaS environments are going to win. And so if you're building a programming environment, build it for the cloud and build it as a serverless environment. So we built such a serverless environment called Apiary. You can go check out the paper on Arvix. So Apiary is a directed graph of Java operations, standard serverless stuff. Develop that application in Spring or your favorite, whatever your favorite environment is. And we compile it into a collection of VoltDB stored procedures with a tiny sequencer for control flow. So that's the way Apiary works. And by the way, just to remind you, I hate to just hammer you over the head, put all application state in the database. If it works for the OS, it should work for you. Okay, so we compared this performance-wise, our stuff, with OpenWhisk and with Lambda, and we're nearly an order of magnitude faster than either of these environments. And the reason is very simple, which is we are optimized, we are the database folks, and so we are optimized for the back end being a database. So if you're running a micro operation in Java and you generate application state, or you want to query the data in your database, you basically, it's one hop into the database and into a stored procedure, one hop back. On the other hand, in a traditional world, such as Lambda, you hop from the application to Lambda and then to the database. So it's 3 levels instead of 2, and that gives you a huge performance boost. And by the way, we give you high availability because the database system gives you that for free. In Lambda, you don't get high HA, you don't get transactions. We give you transactions, so forth. So life is simply better than Lambda, faster, more functional, and life is good. But there's one added benefit that you have to think about for a moment. Debugging serverless environments is a huge pain in the butt because they are fundamentally parallel worlds. And the trouble is, and I'm going to use Jim Gray's terminology here, there are 2 kinds of bugs. There are Bohr bugs and there are Heisenberg bugs. So Bohr bugs are repeatable. So if you have a Bohr bug, that gets very quickly knocked out of most programs. The killer is Heisenberg bugs, which are not repeatable. And so you run them and you run your program. Sometimes it fails, sometimes it doesn't. And in the commercial world, Heisenberg bugs are just dreadful. You put, if your customer is important enough, you put engineers on airplanes to try and figure out what's going on. Now, most of the time, Heisenberg bugs are caused by parallel programs somehow interfering with each other. Well, in our world, parallel micro operations are transactions, and the transaction system will keep them from interfering. So most Heisenberg bugs aren't a problem in this world, so you get a much easier debugging world. So just to say what I already said, micro ops are transactional, HA also. That eliminates most Heisenberg bugs. And Apiary has a really fancy debugger, which you can read about in VLDB 23. So if you can back up the operating system 15 minutes, it's trivial to back up your program any amount of time and then single step it forward. So you can change stuff, single step forward, see what happens. So you get a really fancy debugger to augment the standard C debugger or Java debugger. Okay, so life is just plain goodness. So you want to summarize why DBOS is terrific. it's way simpler than whatever you're currently doing. Linux is gone, Kubernetes is gone, Splunk is unnecessary. Any transactional file system you're running is unnecessary. Any HA that you're doing is unnecessary since all that stuff is built in. So it's way simpler. You can let your Kubernetes administrator go on to unemployment. You have way better security. This is a security world built from the ground up. There's no reason why you have to take a leaky boat and layer a bunch of security stuff on top of it. And if something bad happens, you get time travel, just back up your world and redo it. So way better security, way simpler. Something that I didn't realize at the beginning was that you get if your location state is in 20 different places and you have to merge that stuff into a Splunk log. And that merge is really painful. And that's all built in. You don't have to do anything. And of course, you also get a programming environment that has great properties and especially its debuggability. Okay, so life is good. So then we ask the question, well, does anybody outside of Stata want to run this? And so we spent a bunch of time talking to users. This was facilitated by a guy named Michael Coden, who until recently was the head of the cybersecurity practice at the Boston Consulting Group. So he hooked us up with a whole bunch of BCS clients. And so we talked to a whole bunch of them. And so the themes that rang loud and clear were in scuff shoe enterprises. And I'll give you one example. There's a large distributed conglomerate, and I shouldn't tell you their name, but anyway, they have in total 100,000 endpoints. Think all of their employees' computers, all the factory floor gizmos, all the servers, et cetera, et cetera. They're using, I think, CloudStrike to capture events off of 100,000 endpoints. That's a 7-digit a year subscription. They pass those events into a enterprise-built workflow system that enriches those events with enterprise-specific data. They pass the result of these enriched events into Splunk, another 7-digit a year subscription. They've written a whole bunch of outlier detection rules in Splunk Talk. And if a Splunk Talk rule fires, they have a human analyst look at this to make sure it's not a false positive. And from the time an attack occurs until the time they notice and take action is measured in hours. So they are terrified of ransomware and other bad kinds of things happening. And such things happen with much more regularity than you read about in the paper. Because most enterprises don't want you to know that they just endured a 7-digit or 8-digit loss from being out of operation. So the thing this particular enterprise loved about DBOS was that it had better security, but more importantly, that it could get back up instantly. So, and you can't help but be cheaper than 2 7-digit a year subscription fees. Okay, so that was one place where we got a lot of interest. Another place was the 3-letter agencies. And for obvious reasons, they are very interested in security. Another place where we got a lot of interest was in financial services. And here you can see why in some areas that are moving money around, you would be very security conscious. But a different avenue was pointed out to us by a large regional bank here in the Northeast. And they looked at what DBOS did and they said, you give us OAOO. And I said, and OAOO is once and only once. And so the idea was they have many systems that store information. And so if they want to move money from one system to another, they're typically not in the same database system. And so their idea is you delete $10 from account A in system A, you send a message to system B saying increment system B, you get back a message from system B saying, yep, I did it. And then you commit the transaction. This is the distributed transaction across multiple storage systems. And there's a thing called XA, which is supposed to do exactly that, but a bunch of their systems don't implement XA. So they have that is trying amounts to XA. And it's buggy, brittle, doesn't work very well, fails a lot. And they said, you guys can do this automatically because you're running the message system and you're running the database. So you can do a distributed transaction without doing anything special. So in particular applications and fin services, we got a lot of interest. So that got us interested in seeing if we could do a startup. So we talked to the venture capitalists. We got a bunch of money from two of the VCs, one of which is the Engine, which is the MIT aligned VC firm just up the street on Main Street. And we began operation in April of 2023. And we've been at it for about 10 months. So now I'm going to tell you what to offer in V1 and who we are planning to market to when it comes out next month. So V1 will be coming out March 10th. And what does it consist of? Well, it's basically everything I've said so far, except we did a popularity contest, and TypeScript is much more popular on this class of applications than it is Java. So we moved everything to TypeScript. The VCs were very persistent and very clear, saying you're going to start with the web world, and to sell to the web world, you've got to be open source. And VoltDB is not open source, so we switched to Foundation DB, which is open source. It is not a relational database system. It's a distributed key value store with approximately the same performance as VoltDB. So all operating system data is in Foundation. User data, we didn't think it's such a good idea to say you've got to put your data in a key value store. That isn't familiar to most of the customers that we plan to market to. So it turns out that the elephants, the web guys, in particular Google, Microsoft, and Amazon, are all betting the ranch on Postgres compatibility. So wire compatibility with Postgres. So RDB is wire compatible with Postgres. So is Citus. So is Yugabyte DB. So is CockroachDB, and a bunch of others. So the answer is use your favorite Postgres compatible DBMS to store your user data. And we merge user data and Foundation DB data seamlessly and put it in the data warehouse. Data warehouse in version 1 is Redshift. You can use whatever you want. The reason it's Redshift is that this is an AWS world in the beginning. And if you'd like to try the SDK now, go to our website and you can download it. It's completely open source. Okay, so that's what V1 consists of. It'll be out next month. And the initial target customers that we plan to try and sell it to are cloud startups, because they're not dragging any legacy along. The trouble with legacy is like the large enterprise that I talked to you about. They said, this is terrific, but we're dragging along, gigabytes of legacy code. And to run all the stuff we currently have, you've got to support POSIX. And we said, oof, we may be forced into doing that, but we'd much rather be compatible with next generation standards, not previous generation standards. So next generation is SaaS standards, workflow standards, that sort of stuff. So greenfields are very attractive because they're not dragging legacy around. The three-letter agencies are very attractive because they are willing to move for better features. They're willing to rewrite stuff. And then certain aspects of fin services, and anybody who's an adventurous enterprise who's planning on moving stuff to the cloud, then this is a cloud environment with very nice properties. And from my point of view, let the revolution begin. It's time to retire Linux. It's time to retire Kubernetes and move to something that is much better and next generation. And with that, stop, and perhaps I will have encouraged some people to throw brickbats.
So I'm a database junkie, so appreciate it. But we're not, a lot of capabilities in modern database. How do you compare the kernel database with the very full featured application database?
Something like VoltDB is full featured. And user data in version 1 is in your favorite database system, whatever that is.
No difference.
So you won't see any difference. So the idea is, and we're thinking about, well, let's say we hope users will tell us whether open source is required or not, and will tell us whether if open source isn't required, we can move to VoltDB, and then will users be willing to put their data in that particular database system? Or do we, what database systems should we support for user data? And so we hope to get some information on what there's a saying that says, will the dogs eat the dog food? And so we hope to find out if the dogs will eat the dog food, and if not, why not? Because we have plenty of money to fix it if we need to. Yeah, John?
What about in high performance systems? Do you think that would be another target market?
Sure, but we talked to the CTO of Uber, who said, yeah, this looks fantastic. Can you run 10 million user transactions a second? And we said, yeah, but not on day one. So I'd like to try something that isn't quite so challenging out of the box. But yeah, long-term high transaction rate systems is clearly an interesting world. Yeah.
With DBOS serverless.
Yeah. That's the only thing we do for them. And
They're not going to hear you on the web.
Tell us we've got to support POSIX.
They're not going to hear you on the web unless you're up here. And try to repeat the questions from them.
So the question is, serverless
the-
environment the only way to interact with DBOS? The answer is yes, for now. You've got to do SAS TypeScript. And if the dogs won't eat the dog food, then we'll add Java or whatever. So this is just the initial stake in the ground, mostly to get a lot of feedback on what users are going to require to run this.
I like to run things locally, so I appreciate the cloud. We've gone through this back and forth. Could you run either or combination?
Every database system that I've been associated with, running on-prem is a huge pain in the butt, because every on-prem system is different and maintenance is endless. The SDK runs on your machine.
Okay, I think that part of the problem is, I'm thinking large scale, you're thinking very large enterprise databases. And I'm thinking full range of multi-system databases.
I say, if users demand us to run on-prem, we will. But I'd rather not, and certainly not out of the box, because there's so much variation.
I just don't trust connectivity and always be there.
I understand.
There are a lot of mentions of security throughout the talk. How are we, or you, preventing like privilege escalation from a query that's, for example, supposed to be intended to be modified, application state?
We don't allow we don't allow SQL ingest attacks. So we just disallow them. So you can't change the SQL that's running at runtime.
Okay.
So there's no, yeah, so you have to prepare.
Can we take a couple of questions from the web? One of the questions is, where is the kernel of the OS stored?
Where's the kernel of the OS stored?
That's the question.
So the kernel of the operating system is the database system. So the answer is RDB is stored wherever RDB stores it, and Foundation DB, we store it, in our cloud world.
Second question is, what is the development download?
You get an entire effectively single user system, which you can use for development. And it's on GitHub. And it's completely open source. So have at it.
Third question, you mentioned a microkernel to drive the hardware, provide device drivers for peripherals, and I assume boost each node in the larger distributed system, perform memory management, etc. How does that compare to a traditional OS kernel?
We run Firecracker. So how does Firecracker differ from Linux? Well, it's a very small subset. And the one thing that you said in the question that is incorrect is communication between nodes is handled by us, not by the microkernel, by using our messaging system that I talked about earlier.
Another question, why did you choose to merge Foundation DB and Postgres data instead of having Postgres on top of Foundation's key value store?
That's you, that's not me.
Why don't you take this?
Okay, so the question is, why are we running two database systems? Foundation DB does not support a SQL full function SQL layer, so the architecture proposed by the question won't work right now. We intend to grapple with what to do long-term about the database. And we are either going to enrich Foundation DB with a SQL interface, or if users let us get away with it, we will run two database systems Or if users are willing to run VoltDB and don't care about open source, we'll move to VoltDB or some combination of the above.
Oh, boy.
Can you take a local question while you're,
Repeat the question.
On clusters. More than 1,000. How does the kernel and database deal with all the stochasticity, right? Loss of a host or shifting or kind of pushing that into the AWS fire practice.
oh, absolutely not. The, it turns out that, that Foundation DB, well, the question is, how large a world will Foundation DB run on? We don't quite know yet, but it has HA, it fails over, it's transactional, has all the properties that you want, totally independent of the microkernel. So the answer is bet on the database system.
But with a lot of events, right? These are a lot of hosts, spread across multiple different storage containers. There's a lot of variability, right? So that handle all of these kind of state changes where who's a host or
Well, VoltDB, the prototype, it runs on a beefy cluster. It will run 3 or 4 million transactions a second. And so we expect on big clusters, Foundation DB will run at least that. And so I think how many users will be able to support? We're about to start performance testing to see how much this thing can scale. And to a first approximation, think of Foundation DB as a main memory database system. And so we're not expecting tons of variability, but we'll see. Anything else? Yeah.
So I'm glad, I'm a Python fan because it's event-driven and all that. But where does sort of the SQL type programming fit? In other words, what do you do TypeScript? How do you do the more database programming? Where
There's a SQL interface in Apiary.
but the SQL language itself, I understand select but the rest of the SQL language seems like a little old. Would you use TypeScript for those type of operations?
No. So either run TypeScript, making queries, or we have a conversion between TypeScript hierarchies who flattened it and will issue the SQL on your behalf. That stuff is very slow.
Procedure. Like TSP use that?
No.
Okay. So you don't have that kind of database.
So you write micro operations in TypeScript to talking SQL. That's all server side and it doesn't run as stored procedures right now, but it will soon.
Okay, that's good.
So, and the idea is run rendering in your client, but nothing else.
Right.
And do server side applications, which are then in our world.
We were just supposed to say the only server side language was the SQL program. We use server side TypeScript, that's right.
Right. So server side TypeScript with SQL calls, or your favorite conversion between TypeScript hierarchies and SQL.
Repeat the question.
but part of Linux is about the hardware and device drivers. So I could provide some sort of compatibility, or you will ask users to rewrite.
Okay. So the question is, what about device drivers and all that stuff? That's all in Firecracker. We don't worry about it. And if we move to GCP, we'll use their equivalent of Firecracker. So we're going to stay out of that world, because that's ugly and a lot of work. So anyway, anytime we can save effort, we'll do it every day.
I still have a question. So it's all on top of Firecracker, but isn't it underneath still Linux then?
Well, Firecracker, in fact, has a Linux underneath it, but you can't see it.
So that's okay to delete it out, but you'll have to overlay it.
Linux is leaky because of all the interfaces that you can get your hands on. If it's buried and you can't touch it directly, then it's much more secure. And I would prefer a bottom layer that wasn't built on Linux at all. But we'll see. But I don't want to write it.
Any more questions from the web? Oh. How large of a footprint does the operating system have? And do you need 100 gigabytes to install it? Do you need 50 megabytes, etc.? How much memory do you need to install it?
The answer is whatever it takes to install Foundation DB. The rest of it is very small. And I don't have that number off the top of my head, but it's not tens of gigabytes.
What does inter-process authorization look like? And is there a capability-based architecture?
No. Inter-process communication is a single table in the database. It is permissioned by SQL permissions. And so basically we are betting on database authorization capabilities. If the world doesn't like it, well, we'll do something else.
Okay, what isolation level do your stored procedures use? Do you avoid queuing bottlenecks, e.g. by using skipped locks?
The answer is we do serializability, and we don't use skip locks. Okay, the answer is stored procedures don't interact with. They can call each other, but they block.
And then the next question is your system multi-threaded?
Is our system multi-threaded? Yes.
Provide the tools or things to help people set up the required SQL permissions in order to make sure that their application, the things they want can talk, and the things that they don't want to talk can't talk.
Repeat question.
Yeah, the question is, do we have tools to help you set SQL permissions? The answer is not yet, but if necessary, we'll write them. Sounds like we've been going for an hour, so maybe it's time to declare success.
Okay, thanks. Thanks everybody for coming. And we're going to try to post the slides online and also a recording of the talk online once I get everything together. Thanks again for everyone for showing up.